In linear algebra, the singular value decomposition is a factorization of a real or complex matrix. It has many useful applications in signal processing and statistics. Formally, the singular value decomposition of an M times n real or complex matrix M is a factorization of the form M equals U sigma V, where U is an M times M real or complex unitary matrix, sigma is an M times n rectangular diagonal matrix with non-negative real numbers on the diagonal, and V is an N times n real or complex unitary matrix. The diagonal entries sigma I of sigma are known as the singular values of M. The M columns of U and the N columns of I are called the left singular vectors and right singular vectors of M, respectively. The singular value decomposition and the eigendecomposition are closely related, namely, the left singular vectors of M are eigenvectors of MM. The right singular vectors of M are eigenvectors of MM. The non-zero singular values of M are the square roots of the non-zero eigenvalues of both MM and MM. Applications that employ the SVD include computing the pseudo-inverse, least squares fitting of data, multivariable control, matrix approximation, and determining the rank, range and null space of a matrix. Statement of the theorem. Suppose M is a M times n matrix whose entries come from the field K, which is either the field of real numbers or the field of complex numbers. Then there exists a factorization, called a singular value decomposition of M, of the form where U is a M times M, unitary matrix. Sigma is a M times n diagonal matrix with non-negative real numbers on the diagonal, and V is a n times n, unitary matrix over K. V is the conjugate transpose of the n times n unitary matrix, V. The diagonal entries, sigma I, of sigma are known as the singular values of M. A common convention is to list the singular values in descending order. In this case, the diagonal matrix, sigma, is uniquely determined by M. Intuitive interpretations. Rotation, scaling in the special, yet common case when M is an M times M real square matrix with positive determinant, U, V, and sigma are real M times M matrices as well. Sigma can be regarded as a scaling matrix, and U, V can be viewed as rotation matrices. Thus the expression U sigma, V can be intuitively interpreted as a composition of three geometrical transformations, a rotation, a scaling, and another rotation. For instance, the figure above explains how a shear matrix can be described as such a sequence. Singular values as semi-axes of an ellipse or ellipsoid as shown in the figure. The singular values can be interpreted as the semi-axes of an ellipse in 2D. This concept can be generalized to n-dimensional Euclidean space, with the singular values of any n times n square matrix being viewed as the semi-axes of an n-dimensional ellipsoid. See below for further details. The columns of U and V are orthonormal bases since U and V are unitary. The columns of each of them form a set of orthonormal vectors, which can be regarded as basis vectors. By the definition of a unitary matrix, the same is true for their conjugate transposes U and V. In short, the columns of U, V, and V are orthonormal bases. Example. Consider the 4 times 5 matrix. A singular value decomposition of this matrix is given by U sigma V. Notice sigma is 0 outside of the diagonal and one diagonal element is 0. Furthermore, because the matrices U and V are unitary, multiplying by their respective conjugate transposes yields identity matrices, as shown below. In this case, because U and V are real valued, they each are an orthogonal matrix. This particular singular value decomposition is not unique. Choosing such that is also a valid singular value decomposition. Singular values, singular vectors, and their relation to the SVD. A non-negative real number sigma is a singular value for M if and only if there exist unit-length vectors U in K, M and V and not such that the vectors U and V are called left singular and right singular vectors for sigma, respectively. In any singular value decomposition, the diagonal entries of sigma are equal to the singular values of m. The columns of u and v are, respectively, left and right singular vectors for the corresponding singular values. Consequently, the above theorem implies that an m times n matrix M has at most p equals min distinct singular values. It is always possible to find an orthogonal basis U for Km consisting of left singular vectors of M. It is always possible to find an orthogonal basis V for knots consisting of right singular vectors of M. A singular value for which we can find two left singular vectors that are linearly independent is called degenerate. Non-degenerate singular values always have unique left and right singular vectors, up to multiplication by a unit phase factor a phi. Consequently, if all singular values of M are non-degenerate and non-zero, then its singular value decomposition is unique, up to multiplication of a column of U by a unit phase factor and simultaneous multiplication of the corresponding column of E by the same unit phase factor. Degenerate singular values, by definition, have non-unique singular vectors. Furthermore, if U1 and U2 are two left singular vectors which both correspond to the singular value sigma, then any normalized linear combination of the two vectors is also a left singular vector corresponding to the singular value sigma. The similar statement is true for right singular vectors. Consequently, if M has degenerate singular values, then its singular value decomposition is not unique. Applications of the SVD. Pseudo-inverse. The singular value decomposition can be used for computing the pseudo-inverse of a matrix. Indeed, the pseudo-inverse of the matrix M with singular value decomposition M equals U sigma V is where sigma plus is the pseudo-inverse of sigma, which is formed by replacing every non-zero diagonal entry by its reciprocal and transposing the resulting matrix. The pseudo-inverse is one way to solve linear least squares problems. Solving homogeneous linear equations. A set of homogeneous linear equations can be written as x equals 0 for a matrix A and vector x. A typical situation is that A is known and a non-zero x is to be determined which satisfies the equation. Such an x belongs to A's null space and is sometimes called a null vector of A. The vector x can be characterized as a right singular vector corresponding to a singular value of A that is 0. This observation means that if A is a square matrix and has no vanishing singular value, the equation has no non-zero x is a solution. It also means that if there are several vanishing singular values, any linear combination of the corresponding right singular vectors is a valid solution. Analogously to the definition of a null vector, a non-zero x satisfying x A equals 0, with x denoting the conjugate transpose of x, is called a left null vector of A. Total least squares minimization. A total least squares problem refers to determining the vector x which minimizes the 2 norm of a vector x under the constraint x equals 1. The solution turns out to be the right singular vector of A corresponding to the smallest singular value. Range, null space and rank. Another application of the SVD is that it provides an explicit representation of the range and null space of a matrix M. The right singular vectors corresponding to vanishing singular values of M span the null space of M, e.g., the null space is spanned by the last 2 columns of E in the above example. The left singular vectors corresponding to the non-zero singular values of M span the range of M. As a consequence, the rank of M equals the number of non-zero singular values, which is the same as the number of non-zero diagonal elements in sigma. In numerical linear algebra, the singular values can be used to determine the effective rank of a matrix, as rounding error may lead to small but non-zero singular values in a rank-deficient matrix. Low-rank matrix approximation. Some practical applications need to solve the problem of approximating a matrix M with another matrix, said truncated, which has a specific rank R. In the case that the approximation is based on minimizing the Frobenius norm of the difference between M and under the constraint that it turns out that the solution is given by the SVD of M, namely whereas the same matrix is sigma except that it contains only the R largest singular values. This is known as the Eckert-Young theorem, as it was proved by those two authors in 1936. Separable models. The SVD can be thought of as decomposing a matrix into a weighted, ordered sum of separable matrices. By separable, we mean that a matrix A can be written as an outer product of two vectors A equals UV, or, in coordinates. Specifically, the matrix M can be decomposed as here UE and via the ith columns of the corresponding SVD matrices, sigma I are the ordered singular values, and each I is separable. The SVD can be used to find the decomposition of an image processing filter into separable horizontal and vertical filters. Note that the number of non-zero sigma I is exactly the rank of the matrix. Separable models often arise in biological systems, and the SVD factorization is useful to analyze such systems. For example, some visual area V1 simple cells receptive fields can be well described by a Gabor filter in the space domain multiplied by a modulation function in the time domain. Thus, given a linear filter evaluated through, for example, reverse correlation, one can rearrange the two spatial dimensions into one dimension, thus yielding a two-dimensional filter which can be decomposed through SVD. The first column of U in the SVD factorization is then a Gabor, while the first column of E represents the time modulation. One may then define an index of separability, which is the fraction of the power in the matrix M which is accounted for by the first separable matrix in the decomposition. Nearest orthogonal matrix. It is possible to use the SVD of a square matrix A to determine the orthogonal matrix O closest to A. The closeness of fit is measured by the Frobenius norm of O minus A. The solution is the product UV. This intuitively makes sense because an orthogonal matrix would have the decomposition UIV where I is the identity matrix. So that if A equals U sigma V, then the product A equals UV amounts to replacing the singular values with ones. A similar problem, with interesting applications in shape analysis, is the orthogonal Procrustes problem, which consists of finding an orthogonal matrix O which most closely maps A to B, specifically, where denotes the Frobenius norm. This problem is equivalent to finding the nearest orthogonal matrix to a given matrix M equals ATB. The cache algorithm uses SVD to compute the optimal rotation that will align a set of points with the corresponding set of points. It is used, among other applications, to compare the structures of molecules. Signal processing. The SVD and pseudo-inverse have been successfully applied to signal processing and big data, e.g., in genomic signal processing. Other examples. The SVD is also applied extensively to the study of linear inverse problems, and is useful in the analysis of regularization methods such as that of Tikhonov. It is widely used in statistics where it is related to principal component analysis and to correspondence analysis, and in signal processing and pattern recognition. It is also used in output-only modal analysis, where the non-scaled mode shapes can be determined from the singular vectors. Yet another usage is latent semantic indexing in natural language text processing. SVD is significantly important for solving nonlinear inverse problems where usually a truncated SVD is used as representation of model. An important application is constructing computational models of subsurface oil and gas reservoirs. The SVD also plays a crucial role in the field of quantum information, in a form often referred to as the Schmidt decomposition. Through it, states of two quantum systems are naturally decomposed, providing a necessary and sufficient condition for them to be entangled. if the rank of the sigma matrix is larger than 1. One application of SVD to rather large matrices is in numerical weather prediction, where Lanczos methods are used to estimate the most linearly quickly growing few perturbations to the central numerical weather prediction over a given initial forward time period, i.e., the singular vectors corresponding to the largest singular values of the linearized propagator for the global weather over that time interval. The output singular vectors in this case are entire weather systems. These perturbations are then run through the full nonlinear model to generate an ensemble forecast, giving a handle on some of the uncertainty that should be allowed for around the current central prediction. SVD has also been applied to reduced-order modeling. The aim of reduced-order modeling is to reduce the number of degrees of freedom in a complex system which is to be modeled. SVD was coupled with radial basis functions to interpolate solutions to three-dimensional unsteady flow problems. Singular value decomposition is used in recommender systems to predict people's item ratings. Distributed algorithms have been developed for the purpose of calculating the SVD on clusters of commodity machines. Low-rank SVD has been applied for hotspot detection from spatiotemporal data with application to disease outbreak detection. A combination of SVD and higher-order SVD also has been applied for real-time event detection from complex data streams in disease surveillance. Relation to eigenvalue decomposition. The singular value decomposition is very general in the sense that it can be applied to any m times n matrix, whereas eigenvalue decomposition can only be applied to certain classes of square matrices. Nevertheless, the two decompositions are related. Given an SVD of m, as described above, the following two relations hold. The right-hand sides of these relations describe the eigenvalue decompositions of the left-hand sides. Consequently, the columns of E are eigenvectors of mm. The columns of U are eigenvectors of mm. The non-zero elements of sigma are the square roots of the non-zero eigenvalues of mm or mm. In the special case that M is a normal matrix, which by definition must be square, the spectral theorem says that it can be unitarily diagonalized using a basis of eigenvectors, so that it can be written M equals U du for a unitary matrix U and a diagonal matrix D. When M is also positive semi-definite, the decomposition M equals U du is also a singular value decomposition. However, the eigenvalue decomposition and the singular value decomposition differ for all other matrices M. The eigenvalue decomposition is M equals U du minus 1, where U is not necessarily unitary and D is not necessarily positive semi-definite, while the SVD is M equals U sigma V, where sigma is a diagonal positive semi-definite, and a U and V are unitary matrices that are not necessarily related except through the matrix M. Existence. An eigenvalue lambda of a matrix M is characterized by the algebraic relation mu equals lambda U. When M is Hermitian, a variational characterization is also available. Let M be a real n times n symmetric matrix, defined by the extreme value theorem. This continuous function attains a maximum at some u when restricted to the closed unit sphere x1. By the Lagrange multipliers theorem, U necessarily satisfies where the nabla symbol is the del operator. A short calculation shows the above leads to mu equals lambda U. Therefore lambda is the largest eigenvalue of M. The same calculation performed on the orthogonal complement of U gives the next largest eigenvalue, and so on. The complex Hermitian case is similar. There f equals x asterisk mx is a real-valued function of two n real variables. Singular values are similar in that they can be described algebraically or from variational principles. Although, unlike the eigenvalue case, hermiticity, or symmetry, of M is no longer required. This section gives these two arguments for existence of singular value decomposition. Based on the spectral theorem, let M be an M times n complex matrix. Since MM is positive semi-definite and Hermitian, by the spectral theorem, there exists a unitary n times on matrix V such that where D is diagonal and positive definite, partition V appropriately, so we can write therefore, the second equation implies MV2 equals 0. Also, since V is unitary, where the subscripts on the identity matrices are there to keep in mind that they are of different dimensions, define then, since we see that this is almost the desired result, except that U1 and V1 are not unitary in general since they might not be square. However, we do know that for U1, the number of rows is greater than the number of columns since the dimensions of D is no greater than M and N. Also, since the columns in U1 are orthonormal and can be extended to an orthonormal basis, this means, we can choose U2 such that the following matrix is unitary. For V1 we already have V2 to make it unitary. Now, define where extra 0 rows are added or removed to make the number of 0 rows equal the number of columns of U2. Then which is the desired result? Notice the argument could begin with diagonalizing MM rather than MM. Based on variational characterization, the singular values can also be characterized as the maxima of UTMV, considered as a function of U and V, over particular subspaces. The singular vectors are the values of U and V where these maxima are attained. Let M denote an M times N matrix with real entries. Let Ed_m-1 and Sn-1 denote the sets of unit 2 norm vectors in room and Rn respectively. Define the function. Consider the function sigma restricted to Ed_m-1 times Sn-1. Since both Ed_m-1 and Sn-1 are compact sets, the product is also compact. Furthermore, since sigma is continuous, it attains a largest value for at least one pair of vectors U Ed_m-1 and Vsn-1. This largest value is denoted sigma1 and the corresponding vectors are denoted U1 and V1. Since sigma1 is the largest value of sigma, it must be non-negative. If it were negative, changing the sign of either U1 or V1 would make it positive and therefore larger. Statement: U1, V1 are left and right singular vectors of M with corresponding singular value sigma1. Proof: similar to the eigenvalues case, by assumption the two vectors satisfy the Lagrange multiplier equation. After some algebra, this becomes multiplying the first equation from left by and the second equation from left by, and taking U equals V equals 1 into account gives. Plugging this into the pair of equations above, we have this proves the statement. More singular vectors and singular values can be found by maximizing sigma over normalized U, V, which are orthogonal to U1 and V1, respectively. The passage from real to complex is similar to the eigenvalue case.